Now, let's establish the technical foundation. To understand how the attack works, we first need to understand how web agents are formulated mathematically. The general framework. At a high level, given a website and a user task requires T, a web agent needs to produce a sequence of executable actions to accomplish that task. It's not just one action, it's a series of actions. Click here, type this, scroll down, click submit, etc. The action generation equation. Here, at each time step, the agent generates an action based on three things. First, the current environment observation as T, what the agent sees right now. Second, the task T, what the user wants to accomplish. Third, the previous action AT, what has already been done. The agent uses a policy function pi to decide what to do next. Crucially, the observation ST consists of two components, IT, which is the rendered screenshot image of the website, what the human would see, and HT, which is the HTML content, the underlying structure and code of the page. This dual observation is important for the attack, as we'll see later. After the agent executes action AT, the website updates accordingly, and the process continues. The action representation. Now, what exactly is an action? The agent formulates each action as a triplet, E, O, and V. Let me break this down with the example shown here. E is the target HTML element, like an input field for email. O is the operation to perform, like type, click, or select. V is the value needed, like the actual email addresses, abc@gmail.com. So when the agent wants to fill in an email on American Airlines website, it would type the value abc@gmail.com into the email input field element. This triplet structure is how web agents translate high-level intentions into executable browser events. This formulation might seem straightforward, but understanding these components is crucial for understanding how EIA manipulates the agent's behavior. The CACT framework. The specific agent framework this paper targets is called CACT, which is one of the state-of-the-art web agent system. What makes CACT interesting is its two-stage architecture. Stage 1, action generation. In the first stage, action generation, the agent takes only the screenshot image as input. Notice, no HTML content here. Based on what it sees visually, along with the task and previous action, it generates a textual description of what to do next. Then the output is underlined variables. These represent textual descriptions, not actual executable code yet. For example, the agent might generate something like type the email address into the email field on the left side of the form. This is a natural language description of the intended action. The key point here is that this stage only uses visual information, what the human would see in a screenshot. Stage 2. Action grounding. The second stage, action grounding, takes that textual description and grounds it into an actual executable web event. Now it uses both the screenshot and the HTML content. It needs to figure out exactly which HTML element corresponds to the email field on the left side, and create the actual browser command to type into it. This stage produces the actual triplet EOV that can be executed on the website. It's essentially translating from human-like description to machine executable code. The key feature why we select why does CACT use this two-stage approach? Because it combines the strengths of both visual and structural information. The visual approach is more intuitive and closer to how humans browse the web. The HTML approach provides precise element identification and structure. CACT can also use different large multimodal models as backbones, GPT-4v, LLAVA, LLaVA, variant, etc. Here's why this matters for the attack. Stage 1 only sees screenshots, while Stage 2 sees both HTML and screenshots. The differences becomes crucial. If you inject something invisible into the HTML with zero opacity, Stage 1 won't see it because the screenshot looks normal, but Stage 2 will see it in the HTML content. The attack exploits this asymmetry, as we will see later. Threat model, adversarial target introduction. Now that we understand how the agent works, let's define what the attacker wants to achieve. The paper considers two adversarial targets, each with different levels of severity. Target 1, specific PII. The first target is stealing specific PII, individual pieces of personally identifiable information. This could be an email address, a credit card number, a phone number, or a personal name. Each of these represents a serious privacy violation on its own. For example, if you are booking a flight and the agent types your email abc@gmail.com into a malicious form field instead of the legitimate one, that email gets sent to the attacker's server. The attacker now has your email address and knows you are booking flights, valuable information for phishing attacks or targeted advertising. This is already a severe privacy breach, but it's the easier of the two targets to achieve. Target 2, full user request. The second target is more ambitious and more dangerous, stealing the entire user request. Remember our example, booking a flight from CMH to LAX on May 13 with my email @adversary@gmail.com. The attacker wants to capture this entire sentence. Why is this more valuable? Because it contains not just isolated PII, but rich contextual information. From this single request, the attacker learns you are traveling from Columbus to Los Angeles. You are traveling on May 13. You are using air transportation, and they get your email. This is a complete profile of your travel plans. This is more challenging to steal because the full request isn't typed into any single field on the web page. It exists only as the high-level instruction given to the agent. Traditional attacks can't access this list. Because it's not entered by users directly into web forms. The key difference, the critical distinction is that the full request exposes additional contextual information beyond isolated PII. It's not just about the data itself, but about what that data reveals about your intentions, plans, and behavior. This makes full request leakage potentially more harmful than individual PII leakage. To make this attack realistic, the paper doesn't assume that the attacker has unlimited power. Instead, they define 3 important constraints that make the threat model believable. Constraint 1. No prior knowledge. First, the attacker has no prior knowledge of what the user is trying to do. They don't know the task T in advance, and they don't know what the actions the agent has already taken. This is crucial. It means that the attack must be completely general and work for any user and any task. You can't craft any attack that says if the user is booking a flight, do X. You don't know if they are booking a flight or shopping for electronics. The attack must work across all attacks and users on that website. This constraint makes the attack more harder but also much more realistic. Constraint 2. Website functionality based. Second, attacker can only design attacks using the functionalities available on the website. They can just inject arbitrary malicious code that breaks everything. They need to use normal website features, forms, input fields, buttons to carry out the attack. However, the paper does allow that attackers can invest effort to make the attack well adapted. They can carefully craft the injection to blend seamlessly into the web page's design, style, and structures. The better adapted the attack, the harder it is to detect. Constraint 3. Preserve agent functionality. Third, and this is really important, the attack should not disrupt the agent's ability to complete the user's intended task. Why? Because if the agent suddenly stops working or behaves strangely, the user will immediately notice something is wrong. They will stop using the website, maybe even report it. From the attacker's perspective, this is a failed attack. You want to steal information silently without anyone noticing. The agent should leak the private information and then continue with the task as if nothing happened. This constraint forces the attack to be stealthy and maintain normal user experience. These three constraints together define a realistic adversary who is powerful but not omnipotent. The attacker must be clever about how they design the injection to work generally, blend into the website, and remain undetected while stealing sensitive information. Finally, let's discuss how websites actually becomes compromised in realistic scenarios. The paper represents two scenarios that have real-world precedent. Scenario 1: contaminated tools. The first scenario involves benign developers who unknowingly use compromised development tools. This is actually more common than you might think. Modern web development relies heavily on open source libraries and frameworks. When you build a website, you don't write everything from scratch. You use React for the UI, Bootstrap for styling, various JavaScript libraries for functionality. This is standard practice and makes development efficient. But here is a problem. These libraries are often maintained by volunteers or small teams. If a malicious actor compromises one of these libraries, either by contributing malicious code or by taking over a maintainer account, every website using that libraries becomes vulnerable. The xzlibs example is particularly striking. This is a compression library widely used in the Linux system. The CSIE report revealed that the latest version had been compromised with a backdoor. The vulnerability was stealthy and persisted for a significant period before detection. During that time, countless systems were exposed. The scary part: the developers using xzlibs had no idea. They thought they were using a trusted, well-established library. This is a supply chain attack, and it's becoming increasingly common in software development. Scenario 2: malicious developers. The second scenario is more straightforward but equally concerning. The developers themselves are malicious. Website developers routinely maintain and update their sites. They add new features, fix bugs, improve performance. These updates are normal and expected. Users don't scrutinize every change. Now imagine a developer who wants to make extra money from their position. During one of these routine updates, they could intentionally inject malicious content. Maybe they add an invisible form field with a persuasive instruction designed to trick web agent. To other developers reviewing the code, it might just look like they are adding better accessibility features or improving from validation. The key is that this would appear as normal functionality. It's not obviously malicious code like evaluate malicious payloads. It's HTML element, CSS styling, and JavaScript that looks benign, but it's actually designed to manipulate web agents. Both scenarios are realistic and have occurred in practice. The contaminated tools scenario shows how even careful, security-conscious developers can be compromised through their dependencies. The malicious developer scenario shows how insider threats remain a persistent risk. Together, they establish that the threat model isn't hypothetical, it's based on real-world attack vectors.